Okay, today we're going to look at integrated rate laws, and these are the equations that we get when we take our differential rate laws and integrate them with respect to time. So we're going to take a look here. We're starting there. So this table here is a really good kind of summary of our first, second, and then zero order. So you'll see up here, all right, in the columns, all right, this is showing them. And then, of course, these are our differential rate laws for each one of those. And so what the next thing is showing is that what if we plot concentration versus time, what each graph would look like for zero, first, and second order. And then this has the next one, the integrated rate laws. This has the format, our y equals mx plus b format for the plots that will produce a linear relationship. So what we're going to see is that depending on whether it's zero, first, or second order, there are different values that we need to plot in order to get our linear relationship. And we want that linear relationship so that, again, we can use that y equals mx plus b form of an equation to calculate different things about the reaction as time progresses. So one of the key things to focus in on here is that, all right, if it's zero order, then just plotting straight concentration versus time, that's going to give us our straight line. For first order, we're going to plot the natural log of the concentration versus time, and that gives us our linear plot. And then for second order, we're going to plot the reciprocal, or 1 over the concentration versus time, and that's going to give us our linear plot. Another thing to make note of here is that the slope of this line, when we plot it, is our rate constant. All right. Now, on zero order and first order, the slope is going to be negative. So and k is always going to be positive. So essentially, the absolute value of the slope of the straight line plot is our rate constant. So that's another thing that we can get from plotting our data. And then it gives us, down here is, all right, a new concept to us called half-life. And half-life is the time required for 1/2 of our initial concentration to remain. Okay, so we have reacted half of our initial concentration in the time that is considered the half-life. And so there are some equations here for each zero, first, and second order. One to kind of note is that for the first order reaction, all right, this one here, okay, the half-life is a constant value. In other words, the other two, for zero order and second order, you'll see that A naught is the initial concentration, that the amount that you're starting with affects the half-life. Whereas with first order equations, the half-life is the same. It doesn't matter how much you start with. If it's a 9-day half-life, then it will be 9 days if you start with 100 grams of the reactant, or if you start with 2 grams of the reactant. It still takes 9 days for that to be reacted. Another thing to note is that in this unit, we will start seeing some problems involving nuclear decay. And the thing to note about that is that nuclear decay, those reactions are first order. Okay, so this is the equation we would use for the half-life. Now, if you don't remember the half-life equation, you can always derive it by remembering that at the half-life, which is again written as T sub 1/2, your concentration is going to equal 1/2 of your initial concentration. And that's always true no matter what the order is. So you just remember that, then you can plug in that to the equation and derive the half-life equation if you need that. The other thing to note, as far as the AP formula sheet goes, it does have I know for sure it has the first and the second order equation. It may have zero order, I can't remember off the top of my head, but it doesn't tell you what order goes with each equation. So one of the things you need to be able to do is to remember which plot gives you the straight line for zero order, first order, and second order. Okay, so I did include in these notes, all right, if you are taking calculus and you are interested in how the integration occurs to derive our equation, I do have here the derivation of the first order reaction. Okay, so that's just for those of you as a kind of side note if you're wondering where they come from. All right, so let's take a look at how we get our integrated rate law, how we determine what order it is based on the data. Now, you'll note before we were looking at differential rate laws, our data was a concentration and a rate. Here, your data for integrated rate laws is going to have time, is going to be in your data, and then it'll have your concentration, which could be pressure, could be molarity. You're going to treat pressure exactly the same way as you would if it's molarity. So here, let me clear my, all right. So what we're going to do in here is, we've worked with this before, we have our two variable statistics app. So we're going to go there and we're going to plug in our data. And I've already plugged my data in, so you may want to input your data, pause the video, and get yours set up that way. This is one of the, I guess, things that the HP Prime makes so easy compared to using our TI-84s. So I have some instructions available in the Google Drive for those of you that are going to take the exam with your TI-84. And I'll be glad to sit down and kind of work with you on using those if you would like to do that. This video, we're just going to kind of focus on using the HP Primes. So we've got our two variable statistics. We go to the number view, and that gives us our little spreadsheet. So we put in our data. All right, then I'm going to do plot. All right, and if you remember from before, if you can't see the lines, right, we do view and then auto scale and say okay, and that will get your lines in there. So let's go back and see what it is that I plotted. So we're going to go back to the symbolic view. All right, and so the nice thing about this is we can, like you saw, we had 3 different lines on there. And so what we're going to do is in the symbolic view, we're going to set up. And so our first plot, which is using a blue line, or blue square for that one, we're plotting just straight out C1 and C2. And if you remember, I put in there, I put my time in C1, and I put my concentration in C2. So when I go back, and this is C1, that is our our independent variable, so that's our x, or the first block here, that's our independent column. And so we put C1 there because that's our time, and then C2 for the concentration, our dependent variable, and then it's a linear plot. Then I'm going to go down to the next plot, and again I'm going to have time as my independent, and then I'm going to do natural log of C2 as my dependent, and again linear. So my S1 line is going to be checking for zero order. My S2 line is the one I'm plotting to check for first order, and then going down here, okay, to S3, get it down there, okay. Here I plot again C1, time in my independent, and then I'm going to do the reciprocal, so 1 over C2 is going to go in, and that's going to check for my second order, okay. So again, if I go to plot, all right, so now we can see. Now, you look at that and you're going, oh wow, they all look really, really linear. So how do I know which one it is? Well, that's where we're going to look at our correlation data. And so we're going to go back to the numbers view, all right, and in the lower right corner, you see a little tab that says stats. What that's going to do is it's going to give me the statistics on the data for each of the plots that I did. So if I pop that up, we'll look and see, and what we're looking at is that R squared value. All right, the closer R squared is to 1, the more linear the plot is. And you can see, looking at these, that the plot view wasn't lying. These are all very, very linear. But if we look, S2 is the most linear plot, and that was our first order plot. Okay, so then we want to look at, okay, you want to, if you didn't already do this, we go back to our plot view, and you want to, so if you're not seeing the lines, if you remember there's that fit tab that's at the bottom, and so see if I unclick it, the line goes away, click it, there's my line. So then I go back to my symbolic view after I've done the plot, and if you remember from before, there is my mx plus b equation of the line. And so if I look at that, remember we said it was first order, and so this is mx plus b, so my slope is negative 2.19 times 10 to the minus fifth. Let me write that in there. And if you remember, we said that k is the absolute value of the slope. So for this, my slope is my k value 2.197 times 10 to the minus fifth. All right, and then because this is first order, for first order, the units of k are just s to the minus 1. And I think, let me go back. I don't think I mentioned that, but I think that table, does it have our units for k on it? Yes, it does. That was the one thing I didn't mention. That, again, another benefit of this table, if you look at it right down here, all right, the last column, it has for zero order, first order, second order, the units of our rate constant as well. So it's just kind of a reminder that that's there. All right. Okay. So that's how we know this is first order, and this is our value of our slope. And then if we wanted to do calculations, then we would do, like if it asked additional questions, which we'll look at some that do, we would use the first order equation for that, and using the y equals mx plus b, so we have that we could put that in there. All right, so let's look at another example. So I'm going back to my number view, and I'm going to put my data in, so 0, 50, 100, whoops, go back, 50, 100, 100, 300, and then go back up, 0.01, 0.00787, 0.00649, 0.00481, and 0.00380. Okay, so then again in my symbolic view, all right, I'm going to stick once I put these in, right? So S1 is going to be concentration and time, C1, C2. Then my S2 is going to be time versus natural log, C2. And then my S3 is going to be the check for the second order, which is time versus the reciprocal. So I'm going to hit plot to make it plot my new lines. And again, if you do view and auto scale, that's going to let me see my lines. And again, this doesn't really, those lines are so close together. So really our plot view is just there to make it give me my numbers. Okay, visually you can't really tell on any calculator well enough to determine which is the most linear. So now we're going to go back to our number view, and then again lower right corner there says stats, and we're going to go to our R squared, and we're going to compare the R squared. The one closest to 1 is S3, which was our second order. So this one is second order. And if I go back to my symbolic view, whoops, go back to symbolic and my second order plot, so I'm going to go down to S3, all right, and there's my equation. So my K is the slope, so 0.5431, and it's second order, so it's 1 over molarity seconds. That's my units for my K. Okay. All right, so let's look at, so that's kind of stepping you through the process we go to determine, based on the data, whether it's first, second, or zero order. So now let's look at some example equations. All right, so here, this is giving me a half-life. Looking at the data, it's telling me. So it gives me the half-life. And this is, again, radioactive decay it's a first order process. So we know we're going to use our first order equation. So I'm going to just go ahead and write it. And I recommend that you do that because it is really useful. A naught. Okay. And again, just a reminder, go back up to the table here. All right, and then this second line right under the graph. All right, so there are our equations. Okay, it's written a little bit different. I always write it in mx plus b form, so that's why I wrote minus kt plus natural log of a naught on there. And then so that's the only difference there. I just tend to write it in that mx plus b form. All right, so let's go back down here. Okay. So it gives me my concentration originally, so that value right there, that's my A naught. And it says my current concentration, so that value right there is A. A is current concentration, A naught is the initial concentration. And it wants to know, it's asking how old is the artifact, so it says T is equal to what? Well, if I'm solving for T, I need the K. I need the rate constant. So what haven't I used? I haven't used this half-life. And the half-life equation, T1 half, is 0.693 over K. So it gives me a half-life for the first order process. Then I can use that to find my rate constant. So let's plug that in. So I have 5,730 is going to equal 0.693 over k. So that gives me, go back, let's get back to our function app and our number view. And a lot of times after you've done stuff in stats, if you remember, like when you go back to your number view in your function, you get like this little spreadsheet looking thing. Just hit escape for that, and that takes you back to your regular calculator. So we want to do 0.693 divided by 5730, and so that gives me a k value of 1.21 times 10 to the minus 4. So we're going to plug that in with the other numbers. So I have natural log of it's 0.87 times 10 to the minus 9, and that's going to equal negative 1.21 times 10 to the minus 4 times t plus natural log of 1.3 times 10 to the minus 9. Draw a line here, separate that calc off. Alright, so let's look at these. Now, your natural log button, this is not the log log, but the ln log. Alright, so it's right above the enter key and on the HP prime. So we're going to go natural log 0.87 10 to the negative 9th. Alright, and hit enter. And so that is minus 20.86. That's equal to minus 1.21 times 10 to the minus 4th t, and then plus, and then the natural log of 1.3 10 to the negative 9th, which is going to be a negative 20.46. And so let's see, so I have my negative that, and then I'm going to add that in there. Go back, because I'm adding that both sides. Go over and get rid of that negative. Okay, and hit enter. So I have minus 0.4016 is going to equal minus 1.21 times 10 to the minus 4th t. So that gives me a t equal to, get that, and I am going to divide by 1.21 10 to the negative 4th. Oops, a negative of that. Hang on. Oops. There. And I get 3319.2, and then because my half-life was in years, that means my k, the time unit in my k is years, which means when I'm solving for t, that t is going to be in years. Okay, so let's look at the next question. So here, alright, we've got some data. So I'm going to get back to my two variable stats, and then we're going to put the data in. So it's 0, 1, and 2, and 4. Oops, it escaped. Let's go back. Go down to here, and we want to delete that. Delete that. Go back up. And so I have 0.1, 0.0905, 0.0819, 0.067. Okay, and then again, just a reminder, I've still got those same setups in my thing. So I'm plotting C1, C2 as S1, C1 natural log of C2 is S2, and then C1 1 over C2 is that one. So then I'm going to hit plot to make it do my plot. Alright, and I can actually see these. So then I'm going to go number and stats. Go down, look at my R squared. So that tells me S2 is the most linear, and S2 is my first order. And then I'm going to go back to my symbolic view. Oops, after I hit OK. And go to my first order, which is S2. And so looking at that, go down, right there is my equation. The slope is, the absolute value of the slope is my K. So K is equal to 0.10013. We round it there. Half-life, or if it's first order, T1 half is 0.693 over K, which is going to be 0.693 divided by 0.10013. Here our data was in minutes, so that means this half-life is going to be in minutes. So now I got to go back to my function number and escape to get back to my calculator. So 0.693 divided by 0.10013, and that gives me 6.92 minutes is my half-life. And then here it wants to know, calculate the concentration at T of 5 minutes. So I'm going to rewrite, just as a reminder, minus KT plus natural log of A naught. Alright, I'm solving for the concentration. My K was 0.10013, and it's saying it wants a time of 5 minutes plus the natural log of. Now, A naught, this is concentration at time equals 0. Well, where do I get that? From my data. My concentration at time equals 0 is 0.1 based on my data list. Okay, so I'm going to get a number on this side, and that's going to give me, so negative 0.10013 times 5 plus the natural log of 0.1 and enter. So I get that the natural log of A is negative 2.803. Okay, now, so how do we get just A? Well, we're going to do the inverse process of the natural log. So, and again, I'm going to do the same thing to both sides. So, just kind of write this up here to the side. Do it in a different color. All right. So, if I do e to the x, or e to the x, where the x is my natural log of A, then that is equal to A. So I'm doing the inverse of the natural log to get rid of the natural log there. And so I'm going to do the same thing to both sides. So that means that my concentration is going to be e to the negative 2.803. All right, and the inverse log, it's the same button. It's just use the shift key. If you'll look, you'll see it's in blue on the natural log key. It says e to the x. So I'm going to do shift e to the x. So you see how it pops up like that. All right, and then I'm going to put in negative 2.803 and hit enter. And so that is 0.06063, and that's my concentration on there, which is molarity. And just to kind of do a sanity check on that, see how it goes down. So at 4 minutes it was at 0.0670, and so it should be lower at 5 minutes, and indeed it is. And then now let's look at the next question. So it says, estimate the time required for 90% of A to decompose. Okay, so what does that mean? That means that A is going to be equal to, now think about it, if 90% has decomposed, then my concentration at that time is going to be equal to 10% of A. So 0.1 times A is going to be my concentration at that time, which is going to be 0.1, and then we said it was 0.1 was my initial one. So 0.01 is going to be my concentration at that time. And again, I'm going to plug it into my equation. So I'm just going to rewrite it. Minus KT plus natural log of A naught. So the natural log of 0.01 is equal to negative 0.10013 T plus natural log of 0.01. And let's see what we get. So natural log of 0.01. So I have minus 4.605 is going to be equal to negative 0.10013 T plus natural log of 0.1. So minus 2.30 and negative 4.605 plus 2.3. That gives me a negative 2.305 minus 0.10013 T. And that gives me a time equal to, I want that, divided by negative 0.10013. So 23.02. And again, my data was in minutes, so this time is going to be in minutes for the time. Okay. Alright, let's take a look at this one. And so we're going to put our data in. So we're going back to our two variable statistics and put in our data. So it's 0, 1, 2, 5, 10, 20, 30, 70, and let's go back up. And we have 1, 0.909, 0.833, 0.667, 0.5, 0.333, 0.25, 0.125. Okay, and so now, again, reminder, C1, C2 is my S1 plot. C1 natural log of C2 is my S2 plot. C1 1 over C2 is my S3 plot. And we're going to hit plot. And then I'm going to go back to the number view and hit stats. Go down, look at my R squared values. And this one is second order. So second order. Go back to my symbolic view and down to S3 to get my equations. So that tells me my rate constant is 0.10002. Alright, and that's second order, so it's going to be m to the minus 1, and then minutes to the minus 1 are my units on that. It says calculate the half-life. Alright, so this is, alright, and so it's for an initial concentration of 1. Alright, so let's look at, because I'm not a big fan of memorizing equations. And like I said, I believe that for the as far as half-life goes, that the first order half-life is the only one that is on the AP formula sheet. So again, the key thing we want to remember is at T1 half, our concentration is 1/2 of our initial concentration. That's always going to be true. So here it's that we're assuming that an initial concentration of 1, so my concentration at the half-life is going to be 0.5. So let's look at our 1 over A is going to be equal to KT plus 1 over A naught. And again, just a reminder, all right, where did that equation come from? Back to our sheet and right up here, second line there. All right, there's our second order equation right there. Okay, so let's go back down and, sorry, this makes you dizzy. All right, get that in. Oops, not that small. All right, so now I'm going to plug in. So 1 over 0.5 is equal to 0.1000002. Yes, I really didn't have to carry that out that far. Plus 1 over, and then A naught we said was 1. So solving for my half-life. So, whoops. Well, let's try that again. What am I doing? Oh, there we go. Alright, let's try getting back out. Forgot where I was. Alright, go back up to my function. And then go there. Alright, there's my calculator back. Okay, so I'm going to get, this is going to be 2, just move this over here. So 2 equals 0.1, and let's just go, we're going to just abbreviate that, plus 1. So that's going to be 1 equals 0.1 t. And so 1 divided by 0.1 is 10. So t, and that's t1 half here, is going to be 10, and that's in minutes, since that's what our data was in. Now it says calculate the concentration of B. Sorry, I'm using A's by default, but here the reactant, they call it B. So again, I'm starting with my, and I'll put B, I'll go ahead and put B in there. B is KT plus 1 over B naught. And so here we're going to actually get our data for the B naught. B naught is 1, right? And so 1 over B equals 0.100 times 40. And again, if it did not give you this time in minutes, you would need to convert it to minutes to be able to use it in the equation, since my K was derived from data where the time was in minutes, plus 1 over 1. Okay, so that means, and again, go over here, 1 over B is going to equal 0.1 times 40, and then plus 1. So that gives me 5. 1 over B is 5, which means concentration of B is going to be 1/5 on there. And then this one here says calculate the B, calculate the time when B is equal to 0.1. In other words, and this would be estimate the time required for 90% of B to react. Okay, because B started out as 1. So that would be another way they could ask the same question. So 1 over, rewrite my equation. Okay, so 1 over 0.1 is 0.1. We're solving for time, plus 1 over 1. And so 1 over 0.1 is 10 equals 0.1 t plus 1. So I'm going to get that 9 is equal to 0.1 t, which t is going to be 9 divided by 0.1, so, or 90, and that's in minutes. Okay, and then let's go back up, and so here, if we're looking at, it says how does the total pressure change over time? Well, look here, see how we're going from 2 gas molecules down to 1. So over time, we're reducing the number of gas molecules, so my pressure over time is going to decrease. Okay, so on the next day after we do this intro, you are going to be doing some practice problems in the book, and so I will be creating a video with these practice problems to let you, if you need that extra help, but it's going to be a separate video. So that's goodbye for now then.